If you build with AI, you already know the ultimate friction point in modern development workflows: context fragmentation. Whether you are using a standard command line interface or a web-based IDE, every session operates in a complete silo. The moment you switch from testing an OpenAI endpoint to querying Claude, or even if you just accidentally close a terminal tab, every piece of accumulated context is wiped out. You are back to zero. The immediate fix for this is an Agentic Development Environment, or ADE. Think of an ADE as a harness, a single application designed to unify all of these disparate models and chat windows under one interface. But centralizing your windows only solves the visual clutter. To cure context fragmentation, we have to solve the underlying memory problem by addressing how a naturally stateless model manages state. An ADE's UI is just a wrapper. True orchestration happens on the local disk. To build an agent that remembers, you only need to isolate two files: agent.md and memory.md. These simple text documents anchor the LLM's computational engine. There is a misconception that giving an agent memory requires spinning up a vector database or managing a complex retrieval pipeline. It doesn't. By adopting an open-source architecture, like the one pioneered by the Hermes repository, you can use plain, mutable text files to achieve a highly responsive, low-latency approach to localized memory. Mastering this two-file read and write loop is the exact mechanism that turns a generic, stateless query tool into a self-optimizing, autonomous agent. Let's look at a standard isolated API call. A local CLI sends a payload to a cloud model, receives the response, and the connection is severed. Because the model is stateless, its internal state resets to 0 the millisecond that connection drops. To fix this, we start with the first file of the Hermes architecture, agent.md. This defines the baseline identity of your agent. This Markdown document operates as an immutable system prompt. It physically wraps around every outgoing API payload, creating a structural shell. Inside, you define static parameters: its role, persona, and strict operating briefs, like you are an autonomous Python coding agent. The rules of engagement live here, and they do not change during a given session. While this successfully establishes an identity across multiple sessions, an identity that cannot record new information is incapable of self-improvement. That brings us to the second architectural pillar, the memory.md file. The technical hurdle here is that large language models cannot spontaneously push updates to your local file system on their own. They require a localized trigger mechanism. The solution is an automated trailing prompt. This is a secondary instruction that executes immediately after the primary generation task is complete, but right before the terminal session is permitted to close. The trailing prompt forces the LLM to review the interaction, parsing the context to extract newly discovered rules or optimizations. Once extracted, the model issues a localized write command, pushing those insights directly down into the memory.md file on your disk. It holds your refined user preferences. It logs discovered edge cases and records preferred syntax styles. When you open a brand new terminal tab, the cycle resets. The system parses both the static agent.md file and the newly updated memory.md file, injecting them together into your next outgoing API call. This automated, continuous local write capability provides a compounding context layer that survives across separate terminal sessions. If we zoom out to look at the entire ADE architecture, you can see how these local files connect to external providers. This harness utilizes API gateways, such as OpenRouter, to serve as the integration layer. Because the memory is pinned locally via Markdown files, the state is entirely decoupled from any specific LLM endpoint. This creates a mechanical advantage, the ability to hot swap models. Mid-project, you can detach from a proprietary cloud model and route your connection to an open-source alternative. It instantly inherits the exact compounding context, reading from those identical local Markdown files. In practice, you could use a highly capable, expensive model to establish complex architectural logic for a script, and then instantly swap to a faster, cheaper open-source model to format the final output. Under this architecture, the LLM functions as an interchangeable compute engine, while the agent's persistence lives in the local Markdown files. Fast forward in time, how does this localized memory behave after dozens of complex development tasks? You get a compounding effect. As the agent executes sequential commands, the Markdown file physically expands. The data continually resorts and structures itself to handle increasingly complex parameters. Through this loop, the agent is effectively programming itself to align with your specific logic, coding habits, and project structures. And we achieved this without spinning up a vector database or managing a fragile retrieval pipeline. Using low-latency, plain-text disk storage is a highly efficient, superior starting point for local AI orchestration. This is the complete architectural blueprint: a unified UI routed through an API gateway to an interchangeable compute engine, all anchored by local Markdown state. You can implement this minimalist, two-file read and write loop within your own localized terminal environments today. Reliable AI autonomy depends on the rigorous, structured text files managed on your local disk today.